Hello, my name is Harrison Leary, and this is my Physics 2211 Lab 3. So the purpose of this lab is to examine how both momentum and forces can be split into their parallel and perpendicular components. And we're going to be doing that through a computer simulation of a black hole and star system, and then later we will also incorporate a theoretical ship. So some of the various physics principles we use, there's Fnet equals Fnet parallel plus Fnet perpendicular, so the sum of the components is equal to the whole. Then the gravitational force is equal to the gravitational constant times the two masses over the square of the distance between them times negative r hat for the direction. Then we have dp over dt, which is the derivative of momentum over the derivative of time, is equal to dp dt parallel plus dp dt perpendicular, which is the same concept as Fnet. And then we also have that dp dt parallel is equal to p hat, which is the direction, times the derivative of the magnitude of momentum over the derivative of time, and that dp dt perpendicular is the magnitude of momentum times the change in p hat over change in time. So for part one of this experiment, the parts of the code I changed are on the right here. So we used basic formulas such as position update, velocity update, and so on to calculate all of these components, along with the formulas we mentioned earlier, such as the dp/dt formulas, to solve for all of their respective values, such as all the Fnet components and the dp/dt components. And to solve for the mass of the black hole, we plugged in the formula we see in the second bullet point, which is that Fnet times r squared over the gravitational constant times the mass of the ship is equal to the mass of the black hole. So then for the system in this scenario, it is the star and the surrounding is everything else, which is the black hole and space. And the given initials we have is that the change in time is 1 day, which we will convert into seconds. And the mass of the ship is 2 times 10 to the 30th kilograms. So then here we will see the result of the simulation. So using the formulas we plugged into the code, we found that the mass of the black hole was approximately 1.4 times 10 to the 34th kilograms, and that Fnet equals 8.73 times 10 to the 28 newtons, Fnet parallel equals 3.37 times 10 to the 27th newtons, and Fnet perpendicular equals 8.72 times 10 to the 28 newtons. So you can see that Fnet and Fnet perpendicular are very similar to each other, and the Fnet parallel and Fnet perpendicular should add up to be Fnet, but there obviously is a small source of error as that does not perfectly line up. So the primary source of error is likely due to the use of time steps within the code, where we are only calculating after 1 day has passed every time, which can lead to some discrepancies. So then for part two, the parts of the code I changed are on the right. Basically what we did is we solved for each of the forces acting on both the planet and on the ship, which is going to be 2 of each, as there's 3 bodies, the planet, the ship, and the black hole. And so we solved for all of those. We used the gravitational force formula, and that's all plugged in on the right. And then at the bottom we have our usual velocity update and position update formulas to change the velocity and position. And this is further simplified in the first bullet point. But again, the system now is the spaceship, and the surrounding is everything else, which is the black hole, planet, and space. And our givens are change in time is 1 day, mass of the ship is 7 times 10 to the 10th kilograms, mass of the planet is 9 times 10 to the 28th kilograms, and the mass of the black hole is what we used before. So then our results from this, for trying to find the closest we can get to the black hole without falling in, the initial velocity we need for that after some trial and error, I found to be negative 3.3 times 10 to the 7th in the x direction, and 3.1 times 10 to the 6th in the y direction, meters per second. And the primary source of error, again, is probably due to the use of time steps within the code, which the change in time is 1 day, but also using calculated values such as the black hole that we found earlier could have added a further discrepancy. So what does this mean? So in terms of our calculation of the net force and the changes in momentum, the way we did that, despite them essentially being the same concept, are different methods. So for the net force, we had to use the mass of the black hole, which we calculated, which is what we plugged into the code. But for the changes of momentum, we were able to use the given masses and the velocity formulas to find that. So you can see that the ways of finding these values, despite them essentially being the same, there are different methods. And then for the initial velocity we would need to enter orbit around the black hole, you would need to decrease your velocity in the x direction and increase your velocity in the y direction. The magnitudes of both of those would have to change in that way. And that's all. Thank you.